Record.
Okay, so we all would be dealing with Boolean algebra, and actually in other divisions of ACSL, they do a little more than Boolean algebra. They do bitwise operations that we don't. We're not going to talk about in elementary, but I'm going to, just to show you what those are, right? So, I'm coming in. With computers, as we have talked about this throughout our sessions since the beginning, right? There are computers only know about binary, right? At the very essential, very basic level, computers are made up of switch circuits, right? So in computers, there's just basically bits, binary bits, right? And so these bitwise operation is the most basic thing you can do in computers, right? So what those means is that not means basically a bit flip, right? 0 becomes 1, 1 becomes 0, or true becomes false, false, false becomes true. So not false is true, right? Not true is false. Not 0 is 1, not 1 is 0. And then and or, those are easy to understand, right? If both are true, if 2 bits are both 1, the result is 1. And if with or, if one of the bits is true, is 1, the result is 1, right? That's or. And XOR means that either or, but not both. Okay, so meaning that if they're both false, right, it's false. Both 0, it's 0. Both 1 is also 0, not both, but either one, right? That's XOR. And then in bitwise operations, you can do shift, circular shift, those type of things. We're not going to deal with too much of that. So there's something different in Python, and then there's this order of precedence in bitwise operations, just like we have in regular integer type of operations, right? And so we'll start from here. Boolean algebra is what we're going to go through today. So in Boolean algebra, you're also talking about the same set of, right, similar set of operators, not basically is the opposite of whatever you have, right? Not true is false, not false is true. And end is true if both are true, right? If both operands are true. Or means either one, right? Either one or both. Or is kind of inclusive, right? Either one or both. And XOR is this exclusive or again, right? And then the XNOR is basically the not of XOR, exclusive or. So you have these relationships between these different operations, right? So these are the basic Boolean operators, right? So when we talk about these Boolean values, right? It's basically a Boolean value has or a Boolean variable can hold 2 values, right? Either false or true, right? And then in computers, we generally This is like a convention type of thing. We use 0 for false. Right? It's easy to understand. 0 is false, 1 is true, or not 0 is true, basically. Right? So a lot of times you can see that in computer programming, when people are lazy, they'll just say if an integer, right? In the if statement, they can say if something, and that means if this thing is not 0, right? And so you have these basic operators. You can also consider Boolean values as single bit binary, right? Single bit means it's either 0 or 1, right? It can't be anything else. That's what bits are in computers. So when we talk about algebra, there are laws about doing algebra. These laws are, they're not just made up. They're not made up laws. Okay, they're not. It's not like in human laws. You cannot kill people, right? That's things that we, human made up these rules to, keep order in the society. But in these are natural laws, meaning that these are equal. For example, x and y, right? If x and y has a set of values, right? It could be either true or false. X and y equals y and x. So meaning that you can, if you have an expression, right? It's like in our regular math, if you have x times y, for example, right? The result of x times y is the same as y times x, right? That's a law. That's the same law as here. Commutative law, meaning that you can switch the two operands, right? And you will get the same value. Right? With OR, you have the same feature, right? OR has the same feature. It's like x plus y, right? You can literally think of this as regular math. X plus y and y plus x, you get the same thing, right? So these are easy to understand. And with the XOR, exclusive OR and exclusive NOR, we have the same features. We have the same law applied. And associative law means that if you have x and y and z, right? The order in doing that series of operations does not matter, right? So if you do x and y first, and then the result of that and z would be the same as if you do y and z first, and then you get the result, right? With OR, you have the same law applied. Idempotent law means that if you have two of the same parts, right, in this operation, in these operations, you can just chop one off, right? So x plus x, x or x, is the same as x, right? So meaning that if x is true, x or x would be true, right? If x is false, x or x would also be false. That's what that means, right? And you have the same law. Same law applies. Annihilation law means that if you have x or true, right? If anything or true, then the result is always true, right? There's no, you can't have any other result because you have a true constant here. Then that means this whole expression is always true. Does that make sense?
Yeah.
Any question about that?
No.
Right, and with end, right, if something end false, then this is always false, right? Because regardless of what x is, this whole thing is always false, because end, right, you have to have both to be true to get a result, to get a true result. That's the nature of the AND operator. Identity law is sort of the opposite, or the other way around, right? So X or false is whatever X is, right? That false part doesn't matter. That what matters here is the X, right? So if X is true, right? If true or false, right? True or false, then this whole expression is true. You got a true in that or operator, because with or operator, either one is true, the result is true, right? If both are false, then the result is false, and you get x and one, meaning x and true. I guess you can also, right? You also have that equal to x, right? The reason that we're going through these laws is that the questions come up in the ACSL stuff is basically either, let's say they give you an expression like this, for example, right? A complex expression, the long one. They either ask you to simplify that, simplify meaning, get it as simple as possible, right? As less parts, as little, less number of parts as possible. So in this one, for example, you have 1, 2, 3, 4 parts. Okay, if you can simplify that, meaning that you can make it into less than 4, that's a simplification. And complement law, meaning that x or not x is always true, right? It means if x is true, then not is false, right? The whole expression is true. If x is false, then not true, not x would be true, right? So either one of these got to be true, right? So the result is always true. And with n, the result is always false, 0, right? Because they cannot both be true, right? It's the nature of operator, of the AND operator. Absorptive law is that when you have x or x and y, then this is the same as x, right? And with a not part of x, you get this, right? So we can use these, like oftentimes you'll see these laws applied, because this you can simplify that operation into one part, right? And this you can also basically take one part out of this operation and simplify the whole thing, right? And with this, you also absorb one part, right? X plus y, x or y. We can prove these laws if we want to, like with a thing called truth table, right? We can try that later. But these are the things that we want to remember as part of this section. And then distributive law. If you look at this, you can think of this, if this helps you remember, right? If you're doing a regular math, if you do x times y plus z, right? That that expression would equal to x times y plus x times z, right? That's in your regular math. And that is very similar here, right, in Boolean algebra. And this too, right? If you look at this as a regular math expression, x plus y times p plus q, it would be either these individual components times, right, x times p plus x times q plus y times p plus y times q, right? That would be the regular math. And here you got the same, you have the same law here. Or at least the expression is very similar, right? The same event, essentially. And here with x, x plus y and, x or y and x or z would be simplified to that, right? These are all ways to help you simplify things. And this is a way to, if you have a not operator on the overarching this expression, then this is a way for you to, break that overarching not, right, onto individual components in this expression. Oh, somebody's sorry. Yeah, this is important. This is why it's important to, always be on time, because when I'm in the session, it's hard to notice when somebody comes in late. Okay. Do you all see my screen here? The shared screen?
Yeah.
Okay. So I'm going through the set of laws in Boolean algebra. So you guys have all, I'll go back one page. Here. So these are Boolean operators, right? When we talk about Boolean algebra. Well, it's like in math, when we talk about algebra, you have, operators too, right? Addition, subtraction, multiply, divide, exponential, and all that, right? In Boolean algebra, we talk about these operators, right? Not, and, or, XOR, XNOR. Right? These are the meanings of these operators. So in AND, you basically have to have two parts that are true to get a true result, right, out of that expression. And OR, with OR, you would be true, you would get a true result with either one being true, right? X or Y, either one is true, the whole thing is true. XOR is sort of like OR, but it's exclusive, meaning that you cannot be both true. Okay, so XOR, X exclusive or Y, right, equals to something like this, right? It's X or Y, but not, right, both true. And so we talked about that, and then these laws. Oops, not there yet. Okay, these laws are very similar to the laws you have in regular math, right? In regular algebra. So you have commutative, where you can, switch positions of the variables, right? Or the components in an expression, and the result of the expression does not change. Associative law, meaning that again, the order in those operations does not matter, right? Or if you change the order, the results are the same. So these are the laws that we would have to remember, right? Well, if we want to, do well with the Boolean expressions. But these laws can be proven, right? If you want to prove these laws, we can do that with a thing called truth table. So after going through these laws, we'll show a problem, right? What I will do is I'll break I'll put this to a side. Nope. Did that work? Oh, it didn't work. Oh. Oh. That. Let's see. Okay, what I want to do is to put this on. Is the problem. Sorry for the technical difficulties. Okay, I'll just put it this way. And then over here are the problems that I want to work on. So let's do that. Huh. Okay, never mind. So these are this is a problem, right? Okay, so this is an expression, right? Let me use a tool here. annotative tool. Okay, so this is an expression, right? Is a Boolean expression. And the problem is asking us to simplify this. Okay, to simplify this. And how do we do that? Like we talked about the laws, right? We talked about the laws. These laws, right? We talked about these laws, and so we can use these laws to, for example, there are the De Morgan laws, right? If we have a not operator over on top of something, right? Then we can break that apart, right? And so, so immediately here we have a not that goes across the whole thing, right? So in here we can see that at least there's an operator here, right? Under that not, there's an operator here, and then this is one part, and this is another part, right? And that's how we can break these things apart. So here it's the same expression copied down here, right? And then we can use the De Morgan's law immediately in this one, right? If we have a x or y and not x or y, the whole thing, it is equal to not x and not y, right? That's what we have here, right? So this part here, this part here, this part, oh God. I think I've lost the pen somehow. All right, so I'll just try. Okay, so this is one part, right? This is one part. And then it ORs the other part, which is this part, right? So the next step is break that OR apart, right? It's not X and not Y. That's the law, right? And apply that law in here. So that first part is A and A or B, right? It already has a not on top of it, right? In the original expression. And so that becomes not A and or A or B, right? That's one part. And now the second part becomes B and not A and not the whole thing, right? Well, you look at the part that is under the overarching not, right? It's
then it becomes just not becomes
no, you don't change that part yet, right? You don't change that. It's just that whole part, which is B and not A. Okay? That part you copy it and then that part has a not on top of it now, right? So that is Y, right? That this part B and not A is basically Y, right? You have not Y here now, right? Not X and not Y. And now if you look at this whole thing, right, using the double negation law, that whole thing, you can just take the double negation out, right? So that this part right? I'm parking my cursor here. Left to the cursor becomes X not, right? That make sense? So that becomes this part, right? A and A or B, right? That's the law, right? That's this law. And then we copy this, the next part down as it was, right? And now we can use this law to break that part. But actually, we don't need to do that if we consider what I did next, which is the absorptive law is this, right? X and X or Y equals X, right? Oh, we actually need to do that later, but we need to do this for this step. So we use the De Morgan law, this one again, this law, right, to break this part, the B and not A part, right? So that becomes not B or not A, right? And right, and now the double negation will change this not A into A, right? And now eventually that becomes A and B, not B or A, right? But with the commutative law, this is the same as A or B, not B, right? So that would be the same. Yeah. Remove the connotations here. Okay. Does this make sense?
Yeah.
Okay. So this whole thing in the end is simplified to just A. That's called simplification, right? That's much simpler than what it was, right?
Well, A is having to all the is nothing into.
Right. Right. So this in between these two steps, I basically skipped one, right? Because that one is easy, right? It's the commutative law makes it easy to switch positions. Yeah.
Even if it's B not, can you still do observation? Even if it's B not?
Yes, because if you think about it, not B is what? Is something, right?
It's a girl or something.
Right. You can call it Y, right? You can call Y is not B, right? Because in algebra you can always do tricks like that, right?
So then
You can call one huge part as Y, right? Like you do regular algebra, math algebra, right? You can just, when you've got two parts in an expression that looks exactly the same, you can just use a variable to replace those parts, right? And you can just call that something, Z, right? Because what is Z? It's okay, because in this law makes Y irrelevant, right? So we can just call not B, we can just call it Y, right? And then Y becomes irrelevant, so we can simplify it out. And that's one type of problem that you have to deal with. And the next problem is, find solution. When you do this, sometimes it might be easier to use this thing called truth table. The truth table basically is something like this, because they give you this expression, right? Give you this expression. In that expression, you have two variables, A and B, right? With A and B, with binary, right? Boolean, we're dealing with binary values. They have these possibilities, right? A could either be false or true. B could either be false or true, right? 0 or 1. So you have these 4 combinations, basically, right? Either both of them are false, one is true, right? Or both are true. That's the only possibilities you have with Boolean variables, right? And then you take the parts from this expression and lay them down in these columns, right? So A or B is here, right? So we use one column to do A or B. And then there's A. A is already there, so we would be fine. And then there's not B. We'll just skip one, right? So we just use, I forgot to change that. The expression is actually, the expression is not A, B, not A and B, not A and not B, sorry. So this is the expression, right? We want to resolve, but it's similar, right? I need to fix that later, but we'll do this. I could probably do it now. So this expression is actually like that, right? That's what's here. So we'll put that not A and B here, right? We have the not A here, right? We have the not A here, and then the not A B here, and then the the expression before the final not here, right? So as you can see that A or B is this third column is 1 or 2, right? 1, column 1, or column 2, right? So for or operation, it's when they are both 0, the result is 0. Otherwise, the result is 1, right? That's or operator, right? So these are, simple steps, right? That we use the truth table to create. And then this part not is basically the flip of those bits, right? So 0 becomes 1 and 1 becomes 0. And not A is basically the flip of A column, right? So it becomes 1, 1, 0, 0. And not AB is column 5 and column 2, right? So again, if you look at these two columns, only when both are 1, the result is 1, right? That's the end operator. And then we have this A or B parentheses or not A, B, which is this part, right? Or this part. So that's 4 or 6, right? 4 or 6. Again, what you do is you look at these two columns. Either one is 1. Either one column you have 1. You have 1 here, right? So 1, 0, 1, 0, 1 is 1, 0, 0 is 0, 0, 0 is 0. And so in the end, it's this expression not, right? So that becomes, right, a flip of these bits. You got 0, 0, 1, 1. So what makes this true would be these two pairs, right? 1, 0, 1, 1. Right? Either they're 1, 0 or they're 1, 1. This expression would be true. Right? And if you actually go follow the steps of the previous question problem that we solved, this whole expression also, can be simplified to just A. What that means is that if you look at these two pairs, B doesn't matter to the result, right? Right? B could be either 0 or 1. The end result is still 1. Right? Because this whole expression, if you look at the whole column, it's the same as the A column, right? So this whole expression, again, can be actually simplified to just A. But the question is, they ask you for all the ordered pairs, right? A, B. So A, as long as A is 1, right? B could be either 0 or 1. The expression is 1, right? Is true. So this is what the truth table looks like. You can use this to, solve any complex expression, right? But you might have to, do many columns, right? Because you got to take care of all these parts in a column, right? To not make any mistake, then you have to use more columns to do all those parts, to get those intermediate results before you can arrive at the final result, right? And let me show you one more, right? One more problem, which is the simplification. This one, right? Simplify this expression. Again, this whole thing looks, convoluted, right? A bunch of things. But then you can see the end result is 0, meaning that the whole thing can only be false all the time. And the way that we reach that is, again, using these laws, right? De Morgan's law, we break these. I kind of skipped a couple of steps. I applied this law on both this and this, as you can see, right? So I broke that part into not A, not, right? Not A and not B, right? And then this part becomes not A and not C, right? So I applied the same law on both of these, right? And the other parts are the same, just copied down, right? And then we apply the double negation law to get rid of the double negatives, right? So not A becomes A, not C becomes C, right? And now what I do is I simply just use the commutative law. And so I can move this part over here, right? So that is copied down, right? A and not B. And then not A and C, right? Is this part. I can move it over here. And after that, I can again use, use both of these laws, commutative and associative laws. This one S. So I can just throw away these parentheses, right? Because these are all AND operations, right? AND operators between all these 4 variables. So now that becomes A. I put this A, not A over here. A and not B and C, and then the rest of the expression. And now, because we have this A and not A here, that part is always false, right? That's the complement law, right? X and not X is always false. So now this becomes false and whatever, I don't care, right? That's the emulator law, right? Because it's false and I don't care whatever that is, right? I can just call that x. And this whole thing becomes false, becomes 0. Right? That's how you apply these laws and simplify the expressions. Okay. We'll take a break here, and then coming back, we'll work on some more of these problems. All right.很枯燥，是不是？
How long is the break?
We're gonna do 5 minutes.
Okay, thanks.
5. Okay.我觉得给小孩子们讲这个可能是有点，
对他们一开始，因为他们最主要不知道这个用来干什么。
对，
你没办法，这个必须只能这么讲，只能这么讲。等他学一段时间，等他们接触了其他的一个，哦，都恍然大悟，哦，原来那个是干这个用的。我们小时候不是怎么这个东西过来的啊？这个时候该死记硬背该惯的还是要惯自己，否则的话他们就
不是就是说我尽量的，就是给他们，跟他们就是说在学校里学过的那些，
对，
知识能够稍微联系
很浅显
的。
了，已经很浅显了。您是在废写是吧？您是在废写吗？
我没有，
你在优艺吗？
我在 UM 对，
在 UM
一直在 UM。
哪个部门啊？
我在是那个 Health IT，
这不就是吗？
哦，我跟你说 Use
HITS 嘛。
HITS，
对，你在里面是哪个 team 的？
我是那个，我们那 team 那名字有点怪，其实我们是做数据那个，怎么说呢？我做那个就是现在主要做一个东西就是那个 Splunk，Splunk 实际上就是一个处理数据，然后分析数据、处理数据的一个平台。
我知道，Splunk 我们也用，就是说这个 SPLUNK 是吧？
对，
那个主要是用来监控那个服务器的。
其实不是，其实就是说它是一个完全就是一个数据处理的一个平台。现在我们就是可能用的最多的用户是这个 security IA。
对，
他们实际上怎么弄呢？就是说我们是把所有的那些 log， 甭管什么东西，全收集到这个里头来。然后就是他们去分析这个数据。就是分析这个数据里面有没有什么异常，就是然后用这种方式来，就是说detect， 实际上是一种 detection， 就是说来看这里头有没有什么异常。
我们现在用 Spark 主要还都是用来看这个监控服务器的这个，比如说服务器哪天出了什么问题了，这个
也是一块了，就是说web server 有没有 down， 或者是有什么 slow， 或者是等等这些东西。
做运算的一些 server，
对，有没有什么异常之类的。对。但我是不管那些东西，我是 run 这个东西本身。然后我也做一些就是说 development， 然后在这上面就是说帮他们做一些 app 啊，然后收集数据了那些东西我来做，收集数据，然后放到里头来就 index
log 的
这些东西。
文件格式是固定的还是说不固定的？
就是说各种什么样的数据我们都有，有 database 的数据，有 syslog 数据，有就是说syslog 数据是很大一块 ，database 是一块，然后就是说其他的还有一些SNMP 采集来的数据，然后还有就是说各种其他人就是弄的，就是做出来的数据表格呀、或者是 database 啊什么之类的，我们都可以拿来处理。OK，
好了，小朋友们回来上课了。
Get started.
小朋友们回来上课了。
Let's get started. Actually, hey guys, I want to ask you a question. So here's a question that I have. Okay. This is something that I'm thinking of doing next semester. So this is actually a simple game, right? Have you all played this? This is like a tennis game.
Is it ice hockey?
You can call it ice hockey, or I can call it tennis. It's basically you can move this paddle right on this side, and you're playing against the computer on this side.
The computer.
So it's a very simple game, right? So next semester, I was thinking of doing a class teaching how to program this game or other kind of games. With that, I mean, do you think that might be interesting?
Yeah, I want to a little bit.
More interesting than this
Well,
Boolean
yes.
algebra
Well,
stuff,
yes.
right?
Yeah, it looks easier than Boolean algebra for sure.
Agreed.
Okay.
1,000 times agreed.
So that is a question that I have. All right, now let's get started again. Come on. Okay. So starting again. Okay. What we'll do is like we did last time, right? I have I should have pulled that up. Where did I put it? Sorry, guys. Okay, here. So these are some problems. Make a little smaller. Okay, Boolean algebra problems. 5. You have stuff.
Can I have like a sheet for like the answers?
Okay, I will put. I'm gonna think of a way if I could to put both of.
Maybe like log out the tab.
Huh?
I can you can put it in the tab. I'm gonna put the tab in tab.
Yeah, that's what I was trying to do, but
I have to like right here. Then we can drag it.
oh, let me try it.
And we can move it right. Mouse split. Like that's it for me.
I mean, it should work with this, but somehow it just does not.
If you crop it, you can.
That's really good.
You have to crop it smaller.
Maybe you can just zoom in. Look at the top of the screen, so 30%.
Yeah. So these are all the problems. It's already there. What I want to do is I want to actually put up the those laws.
What does it mean by ordered pair?
Ordered pair means AB, right? AB values. Where's order?
So let's just make
here.
this thing
Here you have AB, 2 variables,
false.
right?
Or B, so does that mean that that's false?
Right. So
That makes it false.
right, to make it false. So A, let's say A is 1, B is 1. This whole thing is false,
What's
or
the
something like all those pairs.
well? It's not there. It's true, and it's and A and not B. It's
Right.
B and not
So
B.
you have to resolve that. Let me get those laws up here. See if I could. Okay. That work?
Mhm.
All right. So right now you probably don't remember all those laws, right? But eventually you guys need to.
What is the asterisk mean?
That's N.
That
Sorry about that.
What's
Yeah,
an
they use all kinds of different,
looks
notations.
sus.
and this tilde thing means not.
The asterisk means and.
Yeah, sorry about that. Yeah, I have to explain, should explain this.
I literally thought it was
Oh,
7 times.
No. In here, it is times. It is multiplication,
Thank you.
but in here, it is n.
You know what true and false is? If you guess and get right,
Right,
you don't even have to do anything.
right.
That's
In here, right, in these, it's
You
n.
can't guess.
This is end, this is end. But that is actually multiplication.
Because if it is a full value, it's add.
Right.
It's a real number. It is.
Yeah, yeah,
Time.
exactly.
So true and false equals false.
It is false.
Right.
Wait, now I'm confused.
Especially
Sorry about
on
that.
a WeChat. in a way. In chat. This is the best day of your life. Look at that.
Okay, so, and these tilde stuff is not.
Yeah, I have a,
It's like true or false, then which law applies. And then denominator, whatever, or identity.
Here you gotta, this one is probably easiest, right? Because you got all the values right there. You can work on those values.
I feel like
Wait, true
How can
or
it be
false, which law should apply?
how can there not be and not A and B plus A and B? So this is one. This is one. And this is one. And it's just A not times A not. So that it's and nothing.
Wait, what's B?
It's a variable. Which makes no sense at all.
Ordered pairs?
Right, here,
So
you-
there's only one.
you, let's say if you want to use the truth table, right? You can try the truth table with number 2. Truth table means you draw those columns, right? Put A and B in there, and A and B is either 1 or 0, right? You have combinations of A and B. So it could be 0, 0, 0, 1, 1, 0, 1, 1. That's all the combinations you have, right?
Does like true or false equal false?
There's no true or false in here, right? Because you have to look at these as variables, A or B.
What does the addition sign mean? Does it just mean adding?
Or
Where? Up here?
No, like on the top and side.
5, it is or.
Oh. Okay, that's so confusing.
Yep,
for
that
some
is
reason-
confusing.
but for some reason I got true or false for number 1.
We can just
Yeah,
guess.
that could be the case.
Sometimes
So
whenever-
which law applies? And or identity?
There's no, it's, let's say 3 plus 5 is what, 8, right? 8 less than 7,
False.
that's false, right? So you put this, you could replace this as false, right? So not false is true, right? So now you have a true or whatever, right? I don't care, whatever is in the
That-
parentheses.
And that was true and false. The parentheses is true and false.
You don't really care because this is true already, right?
So that means
True or something is always true, right?
Isn't there a law where you can change to the same thing and show it?
Right? Because once you resolve this part, you already got the result.
I have
Right?
a question. Is
It's
this
true
one-
or false,
Is it,
true or whatever.
I have a
really.
question for this one. Is it like this or like this? Which one should I kill? From 2 A's and 2 B's? Let's go. Which one should I kill?
You can, right? What you can do there is
What is? Plus 4?
think about it a little more, then we can.
I don't really understand the ordered pairs make up something.
Me neither. But
Have you looked at the,
now I have something.
we went through the, this one, right? Let me find
I have a
that.
question. If I have 2 A's like this, can I kill one? So
No,
whatever-
you look at which law applies.
Yeah, I
right?
know, but can I kill one? This one, or-
So with this, we just went through. This is finding the pairs, right? Finding the ordered
I have a
pairs.
question.
A, B, right? A and B. A is 1, B is 0, or A is 1, B is 1. That would make the expression true.
That's so
I have a
confusing.
question.
Is this, why is this confusing?
I mean,
It's just
the
it's a makeup
expression
of the
isn't
table.
confusing, but they're like.
How do you get, I think it
ordered
from what,
pairs.
I know, but how do you make?
The ordered pairs is, don't think about the ordered pairs first, right? If you look at this, these are ordered pairs, right? A, B, right? A and B can have, A can have either 0 as the value or 1 as the value, right? A binary, a Boolean variable has 2 values. That we established, right? So A can either be 0 or 1. Is that okay? And B can also have 2 values, right? Either 0 or 1. Right? That's what variable means, right? Variables can have any value, right? But when we are dealing with binary and Boolean, they can only have 2 values, right? So it's not like integer. If it's an integer variable, then it can have unlimited number of values, right? From, minus infinity, from negative infinity to positive infinity.
I thought it was to this system.
Say that again?
Rate system processing and
Right.
then lags.
The value of integer could be anything, right? Could be, is unlimited, literally, right? This is the range, the value range of integer is infinite, right? From negative infinity to positive infinity, right? Or if it's a positive integer, it goes from 0 to infinity, right? But we are in here in Boolean algebra, we're dealing with binary. And a single position binary, really, right? A single bit binary. So it can only have 2 values, right? That we have to establish, because when we say Boolean, it means either true or false, right? 0 or 1. Okay, that's all we're talking about. That's what this ordered pair means, right? So let's say if the expression let's say if we're finding the pairs that makes this expression false, then what we get, the expression is false, are these 2 rows, right? When you look at these 2 rows, what pairs make that, gets you those results, right? It would be A equals to 0 and B equals to 0, or A equals to 0 and B equals to 1. No, those are the values that you give to A, right? So if you give A a 0, that means in this expression, if you gave A a 0, then this whole thing is 0. Right? If you give A a 0, B a 0, this is 0. If you give A a 0 and B a 1, this is 0. Right? That's how you evaluate this expression, right? The way you do it is you can just put those pairs into this expression, right? And then that becomes 0, 0, 0 or 0 is what?
0.
0, okay. And then here, not 0, 0 is what?
0.
0, right? Not 0 and 0 is 0, right? Right? And means both have to be 1 for it to be 1, right? Because we're trying to find out what the end value is. Now this becomes 0, right? 0 or 0 is 0. And not 0 and 0 is 0. Right? And then what it is not 0, not is 1, right? And not 0, not is 1. 1 or whatever is still 1, right? And then that negate again, right? You got a negative up here. That gives you a 0 value, right? Or if you can do it, just lay all the values out with all these little, each individual components, right? What we have here is A or B, right? This column is A or B. We calculate A or B. Does that make sense? You know how this column is come from?
Yeah, because A.
From these values, right?
It's
It's A or B.
So 0 or
0 or 0
is
is 0.
0.
0 or 1 is 1. Right? 1 or 0 is 1. 1 or 1 is 1, right?
And then 0.
Or if you read it the other way, false or false is still false, right? And false or true is true, right? And true or true is true. So we calculate all the individual components in here, right? A or B, and then not A, right? We got a not A here, not A and B. We calculate the not A and B here, right? And then we calculate the not A or B, which is this, right? Not A or B. A or B is here. So not A or B is basically a flip of that, right? Not is basically, if the original value is 1, it becomes 0. If the original is 0, it becomes 1, right? That's how you use a truth table. I mean, the other way to do it is literally just put the values in here, right? And then you calculate that. But I mean, this is mechanical. This takes a little more step to do, but it's easier. It's less likely to, you're less likely to get it wrong, right? Once you have all these components, all these individuals in each column, right? You can look at this as this, right? We have A and B. These are the variables in this expression. Right? Does that make sense? And then you can calculate A or B, which is part of the expression. You can calculate that, right? And basically you calculate all the components in these columns, and then in the end you combine them. Right? You do one operation in each column. Basically. Right? This is how many operations you have. 1, 4, right? 1, 2, 3, 4, 5. 1, let's see, 1, 2, 3, 4, 5, 6. I don't know. 1, 2, 3, 4, 5. Oh, yeah, we got 2. That's 1 and 2 are the variables, right? So we have basically 6 operations in here. This is or, and, not, right? So we have 6 operators in there, and we have 6 columns representing all that calculation. Is that? I mean, if you're still confused, just say so. It's okay, because this could be a little intimidating, right? There are a lot of steps in there. Do you know how each one of them is done, right? Let's say this column is not A. Not A means you take A and you flip all the bits, right? I mean, not all the bits. You flip the bit. So if A is 0, it becomes 1. Becomes 1, 1, becomes 0, 1 becomes 0. Right? That's, that's what this is called the truth table, meaning that once you lay out the variables and you do the operations one step, one column at a time, in the end, you will get all the possible values, right, of the expression. So, well, all the possible values are actually just either true or false, right? Either true or false. And the solution that the question asking you to find is to find the pairs that makes the expression true or false, right? Like in the contrast problems, they're asking you to find the pairs that make it false. Does it make a little more sense now?
Yeah.
Okay, so, okay, somebody asked a question here. Sorry. What's OR again? Okay. Yeah, OR is, yeah, plus is OR. Is end also, no, end is the star, right? Yeah, okay. You guys answered the questions, helped each other already, so. So the law and this and yeah. So if we look at this again, the first question, if you look at this, inside this parentheses is 3 plus 5, right? 3 plus 5
Less
less
than 7.
than 7. What is 3 plus 5?
8?
8, right?
8 less than
8
7
less than 7 is
is
false.
false, and not a false is true.
And not false is true. So you got a true or something.
True or false by the two greater than 1.
Really, you don't, like I say, you don't care, right? Because this first part is already true. True or
Anything is true.
anything is true. So this is true, right? Right? Does that make sense?
Yeah.
8 less than 7 is false. Not false is true. Is that?
Yes.
I mean, don't overthink it, right? Because these things are supposed to be simple, logical, right? Boolean algebra is all about logic. Logic means, right? If something is true, it is true, okay? Right? That's logic. If something is true, it is true. If something is false, then not false is true. Okay, that's all there is, right? That's all there is about Boolean operations. And then you get, I mean, these laws are there to help you simplify these. Once you got, more convoluted logic, then the Boolean operator, I mean, the laws help you to simplify those things. But to begin with, right, you only have those three. I mean, the most basic Boolean logic are those three operators. Not, right? Not meaning flip the result or flip the value, right? If something is true, not that is false. Right? If something is false, then not that is true. Right? That's all there is about the not operator, right? And means if both are true, then it's true. Right? That's all there is. So you have two variables, like where is it? here, right? A and B. A and B means A and the B both have to be true. Then that part is true. Right? All right, like this, like the question 3 here, right? It asks you about the ordered pair that makes it true. Then you can, because with A and B, you have 4 combinations, right? 4. Like we talked about in this, right? There are 4 combinations. There are 4 pairs of A and B, right? Either they both are 0, or one of them is 0, or both are 1, right? They're all these 4 are all the possibilities for A and B, right? So each one of those is called an ordered pair, right? A pair of these 2 variables, A and B. And so if you look at this, right, you can use that truth table to do A or B, and B and not A, right? I mean, you
B
could
and not A is obviously,
put these, right?
is obviously false.
You can,
I mean, anything and false is false.
right? Because this one you can actually simplify, right? Not A or B. There's a law for that. That's the Morgan's law, right?
And let's say, isn't it like true?
No, not A or B. A or B could be either, could be, that's an expression, right? Not A or B. If you look at this, which was this, right? Not A or B, right? This says not X or Y, right? It means the same thing. That means that equals not X and not Y. So here you can do not X and not Y, not A and not B, and then NB and not A. Right? Right? And then you use the commutative law and stuff to move it around, because you got all these N. Now it becomes all N, right? You break up this A or B, it becomes not A and not B, and not B and not A, right? And then basically you have not B here, right? You have a not B here and the B here. So B and not B cannot always, B and not B is false, right? And so this whole thing is false, right?
So how many ordered pairs make it false?
It doesn't matter. Then all the pairs make it false, right? So it's 0, 0, 0, 1, 1, 0, 1, 1.
It's 2 because so the answer to number 2 is 2.
How many ordered pairs?
Is it 2
4.
or 4?
Because it's always 0, right? It's always false. It doesn't matter how many pairs you have. So the total number of pairs is 4, right? So it's going to be 4, right? For A, basically all the combinations of A and B, right? A and B could be both 0, could be 1, 0, could be 0, 1, could be 1, 1. The end result is always 0, right? Right. With that, you can actually, and I think with this one as well, you could sort of
It's not A and not B, or A and B.
right, and let's see. Yeah, I think this actually could also be simplified, but it might be easier to do it with the truth table.
Mhm.
Right, this could probably be simple. Well, this is asking you to simplify. So what you do here is this becomes not A and not B, right?
Mhm.
And this becomes
Not E
not A and
and
B.
B. That's 4.
And then you got not B in both parts,
Mhm.
right? And then you can use this this law here, right? You got not B is in both parts, not B, and then there's or in the middle, right? So you can call not B X, right? So you can take the not B out,
Mhm.
and so it becomes yeah, it becomes not B. This is not B. Yeah, we can do this. We're out of time, but let me do this. Um, I'm going to stop sharing and do oh, sorry. A little hard to operate. Okay. Let me try. What's the expression there? We'll just do this one and then we that expression is here. That's that expression, which is not A and not B plus A and B, right? That's the expression, right? And so if we look at this part and using the De Morgan's law, right? This part becomes not A or B, right? Or A and B. Is that right? Let me get the expression right. Yeah, not A and not B, or A and B. Okay, that is correct. Right, that expression becomes this. And what can we do with this? Hmm. I'm a little confused here. So maybe we'll do this next time. Let me think about it, how this could be simplified. We'll do it next time. Melody and Ryan, if you guys are done, you can, again, take a picture and send it to me.
Okay.
All right, thank you. Thank you, guys.